Okay, today we are going to be talking about undamped forcing. So we're going to work through this with a specific example. So we are again having a harmonic oscillator. So we have the second derivative of y with respect to time plus y equals, now note here, we have no damping. There's no dy over dt term. This is going to be equal to the cosine of omega t. So we're going to drive this undamped oscillator with the sinusoidal force. And notice I'm just having an omega in here. We're going to allow this to be variable. Because we want to see what happens when we drive with different forces of different frequencies. Okay, so this is, of course, going to be computationally complicated, but it will allow us to understand what's going on a lot better as we move through this situation. Okay, so what we always do first is we solve the homogeneous problem. And to do that, we solve for the roots of the characteristic polynomial, which in this case is lambda squared plus 1. And we want its roots, so we set it equal to 0. And that implies that we have I as our eigenvalue. Plus or minus I, actually. And this is written in real and imaginary part. This is 0 plus or minus 1 I. Okay. So this, without any damping, this is, of course, a center oscillation, as we call it. It's periodic exactly. And so the general homogeneous solution is some constant k1 times cosine of t plus a constant k2 times the sine of t. Okay? And that t here, that's really 1 times t. It's this 1 times t. Okay? So here, the homogeneous solution has a frequency of 1 over 2 pi, right? It repeats itself every 2 pi seconds. And the amplitude is determined by the initial conditions given. All right. So that'll determine K1 and K2, and that'll determine the amplitude. Okay, so there's our homogeneous problem. Now we need a solution to the driven equation. Right? As long as we get one solution to the driven equation by the linearity principle, we can add any solution to the homogeneous problem to get our desired solution. So going back to the driven equation, we are looking to solve d squared y dt squared plus y equals, now we're not going to solve equal to cosine of omega t. We're going to solve equal to ei omega t. Right, this is the trick we did before. And recall that the real part through Euler's formula of ei omega t is cosine omega t. And that and the linearity of this differential equation will allow us to just take the real parts at the end of this and be happy with our solution. Okay? So that's our driven equation. And of course, the way we've been solving these is we guess that our solution is going to have this behavior. It's going to look like ei omega t. So we're going to guess y is equal to a times ei omega t. Now that's our guess, and now we have to compute with it to figure out the actual constants here. So let's continue and compute. When we have y, right, our guess is y equals a ei omega t. Then the second derivative of y is minus a omega squared e I omega t. That's the second derivative of y. And then remember the differential equation is the second derivative of y plus y. So we have plus a e I omega t. And that's going to be equal to the driving term ei omega t. Gathering like terms over here, we have a times 1 minus omega squared. E I omega t is equal to e I omega t. So that must mean that a times 1 minus omega squared must be equal to 1, which rearranging means that a is equal to 1 over 1 minus omega squared. Great. So going back, then y is 1 over 1 minus omega squared e I omega t. And through Euler's formula, that's 1 over 1 minus omega squared cosine omega t plus I sine omega t. And we take the real part, so our particular solution is equal to 1 over 1 minus omega squared cosine omega t. Okay, so there's our particular solution. We already had the homogeneous solution, so the general solution is as follows. Y of t is some constant k1 times cosine of t plus another constant k2 times sine of t plus 1 over 1 minus omega squared cosine omega t. So that's our general solution. We want to start looking at some pictures and talking about that. So let's pick a particular solution. Let's set y of 0 and y prime of 0. So we're going to start completely still and at the equilibrium position. So we'll have y of 0 equals 0 and y prime of 0 equals 0. When we do that and solve for k1 and k2, we get the following expression for y. Now y of t, we have one particular solution here, equals 1 over omega squared minus 1 cosine t. So k1 is 1 over 1 minus, or 1 over omega squared minus 1. And then we have 1 over 1 minus omega squared cosine omega t. So there's our solution. And because we gave ourselves some latitude and did not fix the value of omega, we can now plug in different omegas and see what we get. So let's go on over to a graphing tool and take a look at what we get. Here we have a command into Wolfram Alpha here. I'm going to plot, this is our y, and I'm going to plot it for these two values of omega, 0.3 and 0.5. Let's see what we get here. Okay, we get a whole lot of mess, right? The 0.3 one is this slightly taller one, and the 0.5 one is the shorter one. But of course, the 0.5 one goes to larger values down there. So we're getting this oscillation. We can see both of these are periodic, not necessarily the same period. Something strange is going on. Let's do another value of omega too as well. Let's add in omega being 0.9. Now that's very close to the disallowed value of omega. Remember, we can't allow omega to be 1 because then we have 1 divided by 0. So let's see what happens when we put in 0.9. Okay, when we put in 0.9, we get this picture here. And the 0.9 value has this weird pattern where we see this like periodic function within a periodic function. We have all these oscillations in the one related to 0.9. But we have this big overall change in amplitude, right? Here the amplitude is large, here the amplitude is small. So let's try to explore that phenomenon. Okay. So looking at that graph, when omega is close to 1, we get interaction between these solutions. This part of the solution and this part of the solution, right? When omega is close to 1, then the cosine of omega t is similar to the cosine of t, and so we would expect them to be working together at similar times, and that's what we get. We get this thing, and this phenomenon is called beating. This is related to if you have two, say, sound generators that have very similar frequencies, you'll hear beating going on. If you've ever tried to tune a guitar or listen to a piano closely, you'll hear beating when the strings aren't exactly quite in tune. We get the sound will get louder and softer, right? So you'll have a certain frequency that you're listening to, and the frequency you're listening to would have to do with these oscillations that are occurring along time here. But then you'd have this volume getting louder and softer, and that would be the beats. Okay, so one question we could now ask is, what is the period, or an equivalent question, frequency of the beats? Right? When we look at this picture, it appears that the larger beating phenomenon will take 125 seconds thereabouts to go through one cycle. Right? We go from largest to smallest, right? So the question is, how do we figure that out? How do we find that out from just these raw answers here? And this is kind of a long story, so get ready here. We're going to introduce some new variables and do some somewhat complicated analysis to figure out what the period and frequency of these beats is. So the first thing we're going to do, and this is completely counterintuitive, we're going to let alpha be omega plus 1 over 2, and beta be omega minus 1 over 2. The 1 comes from a hidden 1 here in front of the t in the cosine for the homogeneous solution, and the omega comes from here. Okay. So this is the average of 1 and omega, and this is half the difference between 1 and omega. Okay. Once we do that, we can rewrite some things here. Now, omega times t, which is the argument of the cosine in the particular solution, omega times t could now be written as alpha plus beta times t, because omega is really the sum of alpha and beta. And then t instead could be written as alpha minus beta times the time. So we're going to substitute alpha and beta in for omega and 1, right? You think, well, why are we substituting 2 variables in for 1? Well, really, there's a 1 here. So we're substituting alpha and beta for omega and 1. And now let's see what we get when we write this out here. Okay. Now y, the solution here, is equal to 1 over 1 minus omega squared times we had cosine of omega t, which recall is alpha plus beta times t, minus cosine of t, which is alpha minus beta times t. Okay, so I've just written y in a different manner, and I'm keeping this omega in here. I don't want to mess with this omega. We'll just let that omega be, because it's not going to interact with anything. It's more of an amplitude. It has nothing to do with the period or the frequency. I could rewrite this. Right, this is going to look much worse as 1 over 1 minus omega times the real part of e to the I alpha plus beta t minus e to the I alpha minus beta t. Okay. That might not look helpful, but we can do a little more massaging here of what we have. We keep the 1 over 1 minus omega squared there. Let's keep the real part here for a second. I can pull an EI alpha t out of both of these. And then I have some stuff left here. I have an EI beta t minus E negative I beta t. Okay. Now let's take a look at this guy here. Right? Now recall, Euler's formula says EI beta t is cosine beta t plus I sine beta t. So when we have this negative here, that doesn't affect the cosine, but it changes the sign to the opposite. And so this difference here is actually 2I sine beta t. So let's write that. 1 over 1 minus omega squared, real part, EI alpha t, times, this difference is actually just 2 times I times sine of beta t. Okay. We're getting somewhere. We're almost done here. So this part is, again, a cosine alpha t plus I sine alpha t. And we're eventually going to take the real part of these things, not the imaginary part. And the real part of this product is actually going to be this term times the I times sine alpha t. So really what we're going to get out of this actually is negative 2 sine beta t sine alpha t. Okay, and let's take the 2 out. We'll go on one more page here and rewrite this as 2 over omega squared minus 1 times sine of beta t. But what was beta, right? Beta was omega minus 1 over 2 times t, and then sine of omega plus 1 over 2 times t. Okay, so there is a new way of looking at our y. Now the advantage is we don't have a sum of sines or cosines anymore. Looking at this term, right, this is omega minus 1 over 2, and if omega is one of these values close to 1, this is going to be a very small number, and a small number corresponds to a large period. This is going to be a larger number, so this is going to be a smaller period. So the larger period is the period of the beatings, and the smaller period is these oscillations happening in between the beatings. We see that right here. This is the one that governs the beatings, and this is the one that governs the oscillations in between the beatings. So if you were thinking about this as a musical instrument, the frequency here would be the frequency you'd hear in your brain, the note you would hear, and this would govern how often the beats are occurring, if that makes sense to you, if you have experience with a musical instrument like that. Okay, so this is the large period, this is the beating is happening here, and the frequency of the beats is, well, it's going to be omega minus 1. It's going to be related to omega minus 1 over 2, which when we put in 0.9, we get 0.05, and then the period, the amount of time it'll take for a full cycle of the beat is 2 pi over 0.5, which is approximately 125. And that is what we see here in this picture. It takes us to 125 to get through a cycle of the beats. So now the other thing we can talk about here is the amplitude. And that's related to this term right here, right? When we have omega large, then the solution is almost unforced. Meaning that when omega is very large, this is a very small number here, and we don't get a lot of oscillation. When omega, however, is close to 1, we get a large amplitude of beating. All right? Let's see what happens when we take omega even bigger, or even closer to 1 in this picture, right? We use 0.9. Let's use 0.99. Take a look here at what we see. And let's also add the 0.9 in as well, just to compare. Okay, so now the 0.9, where we saw those beats before, it's swamped by the size of this. These beats are going to take so much longer to occur, and we get a large amplitude, right? An amplitude much larger than we got before when we choose omega to be closer to that natural frequency of 1. Okay. So that's what happens when we drive at frequencies near the natural frequency, near the frequency that the homogeneous solutions go from. What if we drive exactly at that frequency? We can't use this analysis that we just did here, right? We can't use that because then we'd have 1 minus 1 here, and we can't deal with that. So we have to just kind of start over for driving at that frequency. Right? So here we're going to have omega equals 1. We're dealing with omega equals 1 as a special case. And this is what's called resonance. This is the phenomenon of resonance. So here's our equation, d squared y over dt squared plus y is equal to, I'm just going to drive with EIT, right? We're really going to take the real part here. Because the real part would be driving with cosine. Our guess would be y. We want to guess a e to the it, but we know that that's a homogeneous solution, so it's going to be at e to the it would be our guess. Okay. When we do that and go through the steps, which I'm going to suppress here, we get a solution of t over 2 times sine t. So our solution has this t not just in the sine or cosine, but on the outside too. And what does that mean for the solutions? Well, that's easy to plot. Let's get t sine t. Here, what we get is something that looks similar to what happened when omega was 0.99 here, but this will just keep growing, right? The other one would eventually come back down and have a beat with a very, very large period. But this one does not beat at all. It just continually grows, right? And what would happen to a physical system under this sort of situation? Well, eventually the physical system would break down because these oscillations would get larger than the physical system could contain it. So this would be what would happen when you think of the opera singer breaking the glass, right? When the opera singer sings at the correct frequency, the oscillations of the glass grow larger and larger to the point that the glass can no longer contain the same structure as it had, and it would eventually break. And that's called resonance. All right. Thanks for listening.